Good morning, everyone. So in today's presentation, I'd like to discuss our recent effort to control the strength of material by using electron in the hole. And recently, I have conducting research on the strength of material at the micro and nano scale. In particular, we have performed in situ mechanical testing and the electron microscope observation. And here's the example. This shows the creep bending deformation of amorphous silicon nanomaterial. You can see under electron beam radiation. So, excuse me. It doesn't work.
Your finger is.
Okay. Okay, thank you. So you see under the electron beam radiation, electron beam radiation significantly enhances the creep deformation. So as you can see here, so the amorphous silicon is originally a very brittle material, but it's surprisingly deformed like this. So it behaves as it's like almost like a ductile metal under the electron beam radiation. So in fact, it did not break and it continued to deform. It touches to the substrate. And these are the creep curve of the experiment. You can see the specimen deformed. Specimen shows a very smooth or continuous creep behavior under electron beam radiation. In contrast, under the non-irradiated conditions, the material shows this kind of the creep behavior with intermittent displacement burst. So we can say that the electron beam radiation significantly alter the deformation properties like this. So, however, what is the cause of this intriguing phenomenon? This is my question. An insulator or a semiconductor is irradiated with an electron beam like this. In this case, numerous excess electrons holes are generated inside the material. On the other hand, the basic process of plastic deformation and fracture is the breaking of the bond, interatomic bond. So we hypothesize that the generated electron and the hole altered or affected the bond strength of the material. However, the fundamental mechanism by which the electron and the hole affect the bond strength have not yet elucidated. So the aim of the study is to determine the effect of excess electron and hole on the interatomic bond strength. Now we are conducting a systematic study of the program, and in today's presentation, I focus the most fundamental problem, the shear strength of single crystal zinc oxide, a kind of semiconductor. So to clarify how the electron alters bond strength. An effective way of evaluating the intrinsic shear strength of material is through spherical indentation. So in spherical indentation on a smooth surface, so as schematically illustrated in this figure, so the high shear stress is generated at a very localized region inside the material, not the surface. So this helps to minimize the influence of inevitable defects such as free surfaces and dislocation. So as a result, it is possible to assess the intrinsic or ideal shear strength or bond strength, directly characterize bond strength using this method. And next, I'd like to explain how we control the excess electron holes through electron beam radiation. And focusing the phenomenon of secondary electron emission. A material surface is radiated with the electron beam like this. In that case, the primary electron interacts with many bounded electrons like this, and the bound electrons are released from its original position, and holes are generated. And one of the unbounded electrons is emitted from the surface as a secondary electron. And the ratio of the number of secondary electrons to the number of primary electrons is called the secondary electron emission factor delta. And the delta depends on the instant energy of the primary electron and the instant angle theta. So we can control by adjusting the condition of electric beam radiation. We can change the charge state near the surface of the specimen. And the sample is a zinc oxide single crystal with a purity of 49 or higher. And we use this kind of spherical indenter, diamond indenter. The tip radius is almost 4 micrometers. And which is pressed on the surface of the material, and specifically 0001 surface, which was mirror polished. And the spot near the indented point is was irradiated with an electron beam without scanning to stabilize the electronic state. And using this SEM, and we set the incident angle to 70 degrees indebted to the injecting hole. So in this case, the secondary electron factor is greater than 1. So this experiment intended to create a hole-rich condition near the surfaces. And this is a typical example showing the relationship between load and displacement. And you can see the load is monotonically increases, and then you can see the abrupt increase in displacement or popping events occur in all cases. And this result is under the non-irradiated condition. And also we confirmed the P-pop value, load at the pop wing, is corresponding to the onset of plastic deformation. And under the electron beam irradiation, the strength decreases like this. However, if we stop the electron beam irradiation, the strength restored to the original level before irradiation. And based on the experimental result, we estimated the shear strength or critical result shear stress using the finite element method. And zinc oxide is the wood-side crystal structure, and there are many strip systems. And during the indentation on the 0001 surfaces, the strip system of the basal and the pyramidal strip system are activated. So we estimate the CRSS on both the basal and pyramidal strip systems. And the figure summarizes the result. You can see under electron beam irradiation, the shear strength decreases, but halting the electron beam irradiation, the strength restored to the original level. So we can say the phenomenon is reversible. In other words, the strength of material can be altered rapidly by switching the electron beam on and off. And also we have conducted a similar experiment under various electron beam irradiation conditions and summarized this figure by changing the acceleration voltage and also probe current. And in this study, we evaluate the cathode luminescence intensity, the CL intensity corresponding to the number of excited electron holes generated. So we can consider the CL intensity as a measure of ejecting hole in this case. And the results show you can see the tau CRSS monotonically decreases as CL intensity increases, and then it becomes almost constant. This result indicates that the hole concentration is a dominant factor in strength of retardation because the shear stress decreases as the CL intensity increases. And also there is a lower limit of the strength of retardation. So this may be due to the accommodation limit of hole concentration. So I mean, if the hole concentration increases, the distance between adjacent holes becomes very shortened. So it generates a large repulsive force. So there is an upper limit of the hole concentration at the local region. And also we have conducted a theoretical analysis using the first principle calculation based on DFT to determine the effect of excess electron hole on the ideal shear strength of this crystal. And we created the simulation cell with excess electron hole by introducing an electron or removing the electron from the simulation cell. And in this case, we showed the result of the pure shear deformation for the basal strip system. And this figure shows the radical result showing the stress and strain curve. And as you can see, the hole doping decreases the ideal shear strength, whereas the electron doping increasing the ideal shear strength. And you can see the ideal shear strength is corresponding to the strength of interatomic bond against the shear deformation. So you can see the bond between the zinc and oxide is broken due to the shear deformation. So this theoretical finding also supports the fact that the presence of excess electron hole alter the electronic state and impacting the bond strength. And also this is a summary of the DFT calculation for the several covalent materials. So you can see if we increase the hole intensity, the strength monotonically decreases. And on the other hand, if we introducing the excess electron, the strength increases, for example, particularly for the case of zinc oxide cases. So this result is aligned with the experimental result, where shear strength monotonically decreases as the shear intensity or injecting a hole increases like this. So we can conclude that the reduction in shear strength observed in the experiment is primarily caused by the decrease in the bond strength between zinc and oxide against the shear deformation, resulting from the presence of hole. And this is a brief summary of my talk. So we explore the impact of excess electron of hole on the shear strength of single crystal zinc oxide, and result indicating that controlling the electronic state due to the electron beam radiation can continuously and reversibly alter the shear strength of zinc oxide. And finally, I'd like to provide some perspective of my project. So at first, we focused the very fundamental problems. I mean, the effect we explore the effect of the excess electron and hole due to the bond strength or excess electron and hole changes the electronic structure, and this in turn affects the bond strength of it. This is a very fundamental problem. But as you know, the actual deformation, the fracture is existing the hierarchy of the complexity. And for example, so our recent study, so my co-author, Professor Matsunaga, also presented in another session of this conference, our recent findings where the fracture toughness of amorphous silica dramatically increases by injecting the excess electron to hole as an electrostatic charge. And also, as I mentioned in the beginning of this presentation, the creep characteristic of the amorphous nanosilicon cantilever dramatically changes under the electron beam radiation. So our next goal is I'd like to determine or clarify this kind of electronic effect on this kind of complex structure. Okay, thank you very much for your kind attention.